Good afternoon. So I have some pictures to wake us all up after lunch. It's good to be back in Newark. I did spend 5 very good years here, the environmental clinic. I'll try to do this, I don't have to hold it, at Rutgers Newark Law School. So I have some former clients in the room, then I went over to New York City, and that's what I'm going to talk about. And I think my role here is twofold. One, New York's the densest city that we have in the U.S., so if we can build green infrastructure in New York City, what a lessons from New Jersey, which is the densest state in the union. And two, I'm the realist. So, what has really happened so far in New York City, and what can we really expect out of performance? If you oversell something, it's not going to go very far. And I'm very wary of that, and I do believe that a very accurate picture will be better for green infrastructure and long-term control plans in the long run. It's no surprise that our panel is on green infrastructure, but the whole day is on long-term control plans, and this is one element of it. With that, I will go forward. Here's what I want to cover today. It's a lot, so forgive me if I speak quickly. I'm going to skip over slides, and I'm going to scan through some slides pretty quickly, because what I want to do is just spend a few minutes on background, just so to orient you, but really go to the section part of our topic here and get to some of the results we have, and that hopefully will lead to some interesting discussions in the afternoon. So Green Infrastructure Plan in New York really grew out of an overall city sustainability plan. Working on Plan YC is what actually brought me from Rutgers Newark Law School over to New York City to work on that, and I did go over to DEP and work on the Green Infrastructure Plan, among other things. And this is a planning phase, right? What I'm going to talk about today is when you build something and you've monitored it, what does it show? But with some preliminary estimates, this is what we were looking at, was really two pathways: continuing on gray infrastructure strategy, or fine-tuning it really with some green. A few lessons here. So you see here, 30 billion, just to orient you, 30 billion gallons of CSOs in New York City every year, on average. This is what's been done so far. This is what's planned, and then how do you reduce it? These are the steps. There are a lot of potential tanks, tunnels, sewer, wastewater treatment plant expansions planned. That was going to get us to about a little short of 20 billion gallons. We took an alternative pathway. So again, we're talking about, this is the bulk of the gray infrastructure, plays a huge role, as you can see here. This is, what can we do with reduced flows? Water conservation, less base flow in the system, more storage in the plants, can have a tremendous effect. Actually, the biggest effect of what we did. The second biggest effect was green infrastructure. I'm going to spend time talking about that today. And this is system optimization. And really what we looked at were a few things. One was cleaning, and one was a tide gate repair system, get less salt water into the system in a tidal system. So this looks better. That's great. So good. So far, so good. Blended strategy. Nothing's by accident. You see we have the gray and the green. Blended strategy here in that bar. What's it going to cost? We did estimate that the all-gray strategy, as we called it, was going to cost about $6.8 billion. The blended strategy, about 5.3. And what's interesting to note about that is the green infrastructure commitment is $2.4 billion, but almost $1 billion, or $900 million, is coming from the private sector, we thought, in connection with new development, redevelopment standards. Put those standards in place over a 20-year plan, life cycle of a plan. You'll slowly build in. When you build a new office tower, I just passed some, glad to see it, it's happening in Newark now. Got some new buildings coming in town, they should have green controls. It's just cheaper to do at that time. There is a retrofit obligation, so when you look at just the public commitment, the green blended plan is about $2.4 billion cheaper, again, over 20 years. We're talking big numbers, but we're also dividing it by a number of years. We also considered, what else do we get for this? And this is an attempt to quantify the co-benefits or the additional benefits that Chris just mentioned, depending on your assumptions about how much green is going to be in your planted areas and the like. We estimated that over time you'd have some $130 million to $400 million in additional benefits. And this is really what kind of pushed us over the edge for Mayor Bloomberg alike. This is the kind of things we're talking about. I won't belabor this, but these are actual projects in the ground. These are not renderings. So you get to take your playgrounds, work with Trust for Public Land in our case, convert them to green spaces, more usable space. It's wonderful, and it's built to absorb stormwater. You've got right-of-way bioswales. This is a schematic. You can see it's designed to absorb water flowing around the that triangle of water along the curb, in, maybe some goes out, most of it goes down, you're building green. A quarter of these makes can increase property values. Actually, we found in the Blue Belt area in New York City, property values have gone up 30% in areas where we've built those engineered wetlands. This is one of our grant program recipients. This is an acre green roof that's actually used to grow vegetables for restaurants in New York City. This is right in the Brooklyn Navy Yard. And it shows the number, not only co-benefits to the system of having green roof that's cooler and some additional economic activity, but they put in a lot of money for this. And overall, the grant, there's been 3 years in the New York City grant program. DEP has committed over $11 million to fund 29 different projects. That's been matched by $5.6 million in private funds. So that's a pretty good leverage if you think about it, and it's going to take 13 million gallons of stormwater out of the system. We did build it into a CSO consent order modification 2012. There's a few important parts here, but what I really want to emphasize is the structure. It's an adaptive management structure. You build things, you test them, and that's what I'm going to talk about, and then you refine it over time. Every 5 years, there's some decision points. And that's really what's critical. There's some commitments made to hit a 2015 timeline, both in terms of dollars and level of effort, and that's what I'm going to talk about. But that really emphasizes this fact that you're going to have these 5-year check-in periods, underscores the importance of monitoring and accuracy. And another reason you want to make sure and you want to quantify how much a certain technique works is to assist the private development community, because they have to comply with this, the new stormwater performance standard. It's in place. It applies to new development, certainly, or redevelopment over a certain value of the building, and that's very critical. New York City has made tremendous progress towards that 2015 milestone. There's multiple city agencies that have contractors underway. That includes the Parks Department, Economic Development, and of course DEP, who has design engineers, construction management, everybody on board. They're mobilized in the street, and they're hoping to hit 6,000 bioswales in the ground by the end of 2015. So the question, I think, for us today is, what is the impact going to be? It's going to take some time. Let's look at what we have so far. These are the sites that have been monitored, different variety, different places, largely in Brooklyn and Queens, some in the Bronx. None in Manhattan and none in Staten Island, which is largely separated sewer area. We use a lot of equipment. Enough said about that. I'll skip over it. Our approach is really to look at, just do a mass balance. What comes in, what goes out. There's some interim measurements of what the ponding level is, what the soil moisture is. It's very important. A few things are important. Want to get good data about the surface area that's draining into that. We call that the drainage area, and you'll see the impact of that in a minute. Soils at each and every site, because it's highly variable. We had sites next to each other that drain very differently. And also weather gauges. You get microclimates. A city like New York, it's not the biggest city, it's not a Houston or an Omaha or one of these cities, or Anchorage with no zoning and the like, it's constrained, but there's variation in the sites, so you have to be pretty accurate. I want to talk about one technique called blue roofs. You heard a lot about green roofs, but blue roofs we think are a much more cost-effective method, running on the order of $5 to $10 a square foot versus 20 to 40 a square foot for green roofs. Very simply, it's a way to store little dams. You can see here, there's a few different methods we checked out. One was a little weir on this inlet, roof inlet, so water will pond up and then drain slowly over time. These little check dams are about 2 inches tall, ballasted, little holes pouring in them, so water will slow down as it gets to that drain there. And then this tray system. We just went out and got some baking pans. Very simple. Drilled some holes in them, ballasted them so they wouldn't blow away, and voila, you've got a system. Well, what does it do? This is a complex graph, and I know New Jersey Future is going to make this available, but I want to describe what you have here, and this is true for all the graphs we're going to go through. You have the rain intensity up here. You can see spikes in rainfall, right? Total rainfall over time of a particular storm. This is a 1.3 inch storm, June 2012. And what happens? Uncontrolled, right? The red line, and then the check dams. You can see here. And so this is the benefit. This is a detention system. It's just delaying it over time. So for each peak, this is what's coming out into the system. And you can see the check dams actually had the greatest benefit. here. In all, we tested about 70 storms. And here's the results. Tremendous volume reduction here. Even though these were designed for peak shavings, as I mentioned, the trays had the most consistent results with about a 50 to 80% retention. So what explains that? Essentially, you have a lot of evaporation that's happening over the life of the storm. Pretty tremendous. Peak flow reduction, of course, this is what it's designed for. All types provided good peak shaving. Again, the tray system, pretty simple, was the most consistent, about 80 to 100% reduction of peak flows. And the way to read this chart, got the tray system right, is peak reduction for rainfall intensity. That's a pretty intense rainfall. 4 inches per hour, that's a very intense rainfall. And you can see they did a pretty good job. You are always going to have outliers in data sets, that's why it's important to get a lot. But you can see here, it did a pretty good job. Permeable pavement. This is a bus depot in the Far Rockaways, very good sandy soils, okay? The subsurface was designed with 18 inches of gravel storage. We used 3 different techniques here. Native soils have a permeability rate of about 6 to 7 inches per hour, so that's the best you're going to get, pretty much. And we used 3 different types: porous pavement, standard asphalt, and a proprietary system called filter pave. There's a lot out there. It's basically crushed glass. This is what we found. This system did well. Hats off to the folks who designed it. 100% capture. Porous asphalt did pretty well for smaller storms and tailed off. Of course, standard asphalt, pretty much 0% capture. That's interesting. Maybe it's just a slow rainfall, right? That evaporates over time, gets captured in those little nooks and crannies. But you can see porous asphalt did a pretty good job capturing about 50%. There was some wear and tear issues with the filter pave, though, so I'm not endorsing any particular technology when we tested it out. I think they're toying with it, but certainly that's the kind of thing that you want to test over time. You don't want to design things that last just a year. This is built in a public housing area, New York City Public Housing Authority, NYCHA, Bronx River Houses. Obviously, it's in the Bronx. Variety of different techniques. We're going to talk about 2 here. The first is underground storage, detention and infiltration, chamber system, perforated pipes. Here's the results. We found that the chamber system did really well, both in terms of volume retained and peak flow reduction. Tremendous result. The perforated pipe system didn't do as well, but when we drilled down to it, what we found is that the difference was not so much the technology as the underlying soils. And this is on the same site. So again, it just shows that we had better soils underlying the chamber system, and that's why it drained. Same site, different technique, rain gardens, little U of rain gardens. You can see here, again, what we did was, let's see if I can show you. There's a walkway and there were gardens. And what we did was we just sawed through the curb, created these little inlets, this little area to, clean out area, and then we excavate. It's hard to see, but the elevation goes down. That's kind of carved out with some backhoes, and then we planted it with plants that make sense. And you can see here, once the plants are established, it looks beautiful. This bed shows it better, that storage area right there. The residents really appreciated this, actually, and beautified some areas that were behind fences and not accessible and not particularly well maintained. What we found is an 1.5 inch storm, again, May 2012. It shows a brief overflow during the high levels, but basically it all infiltrated within 3 to 4 hours. This capture here is not quite 3 to 4 hours, but it's pretty good. You can see that intense storm here corresponds on the hydrograph with tremendous inflow into the system. This is the overflow height. It was just too much for it to handle initially, but then you have the ponding depth in the green line here, some peaks in the overflow, and then basically, more or less, no outflow through what we're monitoring. That just represents what couldn't get into the system. So pretty good. Overall, how we do, here's 4 bioretention areas. You can see pretty good 100% capture rate at all those. I do want to draw your attention to this chart. You'll see this when I get to it. For more time I do. This is the drainage area ratio to the green infrastructure, 7 to 1. So basically, got an area of 7,000 square feet going to 1,000 square feet. Wide variety here, pretty conservative spacing actually, just depending on the pathway ratio. 17:1 did pretty well though. So that's good news. Again, the key is what's going to happen over time. On a somewhat larger scale with a footprint of 11:1, we took a highway median, pretty similar technique, looked at 83 storms. You need to monitor over a few years. 2011, of course, the year of Irene, was a very, very wet year. You can see pretty intense storms. I mean, we had nearly an 8-inch storm that year. What we found, and this is a 2.5-inch storm, pretty intense, was that the overflow grate level was reached, is the conclusion for this, but only a little overflow occurred. These are all designed to drain down in 8 hours so you don't have a mosquito problem. Very easy to calculate how you do that. You can see it did very well. Here's another way of looking at it. You have the volume retention, nearly 100%. It's only had 4 overflow events since the installation. So it's very effective. Now, there's not too many places in New York City. You have a highway median. This is way out in Queens. But you have to be opportunistic. More commonly are these enhanced treat pits. You can see standard dimensions, 20 by 5 by 5 deep. And the depth is obviously very important to have that gravel storage area. We looked at some of these. You can see here, standard hydrograph. This is a 1.5-inch storm. I want to roll up to what we looked at and point this out. This is intentionally over-designed. Remember, these are pilots. 99:1 ratio. It doesn't do too well, but it does something. When you have 39:1 ratio, again, pretty extreme. It does do, there's some storage. When you get to the 11:1 ratio, it does pretty well. This one did very poorly, bad soils on the slope and the like, but it's important. Here's another cadre of 10 bioswales monitored over 185 rain events. They did pretty well in managing storms of 1 inch or less, which was the design standard we were shooting for. I do want to quickly speak to, and I'm over by a minute, so I'm going to skip a whole section of my presentation, but this is important. The question is, they work on an individual basis. How do they roll up? Because ultimately, you're looking at a citywide basis, right? So as part of the consent order, what we designed was 3 neighborhood demonstration projects. 23 acres, roughly a little bit more than 20 acres. One's 23 acres, one's 24, one's 16. And we looked at those in different boroughs. The approach was basically to pick areas that drain to one point in the sewer, monitor it before construction, monitor it after construction. Okay, so far so good. Now, of course, the rainfall during those periods, pre and post construction, aren't going to be exactly the same. So there's some, modeling involved and the like. But we did have rain gauges for those. The pre-construction monitoring period is 13 months, 17 months post-construction. And all of this is available online. Go to New York City's website. They have monitoring reports they publish every year. Here's the design. You have these, individual bioswale areas. You can see the sewer flow here. It's all draining to this main, not quite a trunk sewer here, and then that's the monitoring point right here. So it's capturing everything. Rain that falls there, that works into the sewer, will be here. Similar design for the other place. You get a plot graph, but when you look at it, it does make sense. When you look at the rainfall over a year, pre and post construction, we see a pretty demonstrable shift in the percentage of rainfall flowing in the sewer. So you might have 80%, now you have 50%. So you could call that a 30% reduction. That's still being refined over time. This data is not quite, as robust. Some preliminary conclusions. Source controls can have benefits for storms that should be less than 1 inch. My mistake. And that's very important. So less than 1 inch. Bioretention source controls can fully retain the volume of 1 inch storms. Underlying soils are critical. And so you are going to have quite a bit of soft costs involved. Even if you simplify design, you don't have design costs, you're going to have site assessment costs when you're putting these in. There's no way around it, and it's certainly worth proper siting. Source controls designed primarily for detention, like those blue roofs I mentioned, can also have retained runoff volumes. Porous pavement, I think is very promising. Certainly road area is pretty important. You have to worry about underground infrastructure, and there can be some results. I do want to say you have to ultimately get these into long-term control plans. I'm going to leave it at this slide, even though I have more, but this is what you're looking at. You really ultimately want to get at a green infrastructure plan where you are targeted, precise about the impacts and the location. You have to roll it up, and that does require a little modeling at the outset, but I'm going to leave it there, save the rest of your questions. Thank you all.